We never got to finish the rest of 1.4 yesterday. Looking at the class notes from yesterday, I can see that we did about 3 examples on simplifying difference quotient to find the derivative using the limit definition. So that's why it took us so long. You can see we spent a long time simplifying difference quotient for each problem, but we did get to talk about what that means, that we found the slope of a tangent line. But what I will do in this video is I will do one more example. Example number 4. I said we never got this far, so I'll record the rest of the lesson and post it on Canvas. So let me start with example 4 in this video, and I'll come back and talk about the other half of section 1.4. I'm talking about 3 different cases of where a function is not differentiable. So, and I also gathered some homework problems, my lab homework, if we have time. We obviously ran out of time, but I think they are great problems, so I do want to talk about them in videos. So here, let me start with example number 4. Oh, emails. Okay, so it says find an equation for the tangent line to the graph of g of x equals 3. Well, it's not 3x, it's square root of 3x. So I need to find, well, I'm going to go ahead and write down what I have first though. They gave us that the x value is 12. So I'm writing this because in order to find an equation of a line, equation of a tangent line, I need x, y, and the slope. That's why I wrote these 3 things on the left. When x is 12, let's find what y is. y1, y value, is what we get when we plug in 12 into g of x. So what will that be? I have to do 3 times 12, and that is square root of 36. So we get that the y value is 6. We need to find the slope. To find the slope, we need to find g prime of x. We need to find the derivative. So the goal is to find the derivative function and plug in 12 in there, okay? Finding this g prime of x, and that's going to take the majority of our time because at this point in our lesson, in our course, we do not know any other rules but the definition of derivative using the limit, okay? So let me write down what g prime of x is. G prime of x is the limit of the difference quotient as h approaches 0, and the difference quotient is what? Oh, not f, I'm sorry. Let me go ahead and change it to g. G of x plus h minus g of x divided by h. All right, let us find the simplified difference quotient first, and then we're going to plug in h equals 0. So limit as that h approaches 0 of this difference quotient. So the function is square root of 3x. So if I plug in x plus h in there, I will get square root of 3 times x plus h. And I have to subtract g of x minus square root of 3x all over h. If you watched one of the video from last week, I explained how we can simplify this difference quotient. We are going to use that multiplication pattern, and I'm going to multiply the numerator and the denominator by the conjugate of this numerator. Why do I have to do that? Because if I plug in h as is, the bottom of the fraction will be 0, and that is, we can't do that. That's undefined. So that's why I'm going to multiply the numerator and the denominator by this. Take a look. I'm going to just copy this exactly the same, but changing the sign in the middle to plus. But I can't multiply that just to the top of the fraction, so I'm going to multiply that to the bottom of the fraction too. Because that is, this fraction, I mean, it doesn't matter how ugly it is, it really is just 1. Because anything divided by itself is 1, right? All right, let us do the multiplication. This part. Think of this as a minus b times a plus b, right? Note, a minus b times a plus b is equal to a squared minus b squared. And why is that significant? Because squaring will cancel out the square rooting, right? So let me erase these so that I can, and let me erase these highlights too, so that I can see what these are. But this, I'm doing that a minus b times a plus b pattern, okay? So I will have to square both these radicals, and when I square them, the square roots will just go away. So what will I have? I will have 3 times x plus h out, and then I will have minus 3x, right? Oh no, I think I made the fraction bar a little too long. I don't need all that. I'm just gonna do this much. But what just happened is that these radicands just came right out, right? Because when you square the square roots, the radicands can just come out because the square root cancels out. And I made sure to connect them with the minus sign. The denominator, unfortunately, is not going to be that pretty. I have to multiply the denominator of the first fraction, which is h, and I need to multiply this by the denominator of the second fraction, which is all that. So I will copy this, and I'll put it inside here, okay? Okay. All right, let me keep on going. This equals limit as h approaches 0. This part is just waiting because I'm not ready to substitute just yet. All right, let me distribute the 3. And I think a lot of things will cancel. Well, probably not a lot, but still. I will have 3x plus 3h minus 3x all over h times. I don't want to write this down again. Let me just duplicate this in the parenthesis, right? All right, what cancels out? I see 3x and negative 3x canceling out. Oh, I see one more. If I do that, the only term that I have left on the numerator is 3h, right? I'm dividing 3h by h, so h cancels out too. So we have our simplified difference quotient. Only thing that it's left on the numerator is 3. The denominator, the h got canceled out, but this mess is still down there. Okay. Now we are ready to plug in h equals 0. When h turns into 0, we will get square root of 3 times x plus 0 plus square root of 3x. So let us simplify that. That is 3 over square root of 3x plus square root of 3x. Well, we're adding same square roots together, so I can just say that is 2 of those square roots. So this is g prime of x. What we need to do here is we need to plug in. I forgot the x value. It's so much work. I forgot what we are plugging in. So let me go back up and take a look. What do we have to plug in? X of 12. So let me plug in 12 in here, because what we are about to find is the slope of the tangent line at x equals 12. I have to do 3 over 2 times square root of 3 times 12, which is 3 over 3 times square root of 36 3 over 3 times 6. For some crazy reason, I changed that to 2. And I should not have done that, right? 2. So that is 3 over 12, which is 1 over 4. So we found the slope. This is the slope. So what I now need to do is write that number down over here, 1 over 4, and I am ready to do my point slope form. Let me copy this on a separate piece of paper. I'll copy this, and I will add a piece of paper down here because I don't want to squeeze my final answer in a small room. So I have my numbers that I need to plug in to write an equation of a line, and I'm going to use the point slope form, okay? Which is y minus y1 equals m times x minus x1. That will turn into y minus 6 equals m times, whoopsies, I know what m is. We did all that hard work to find that m of 1 over 4 and x minus 12. So I believe this is the tangent line. This is the tangent line at 12, 6, x equals 12. So I'm going to confirm this. I'm going to confirm if this is correct. Let me open up a Desmos graphing calculator on my iPad. I will type in the original equation, which was g of x equals, I'll just say y equals square root of 3x. Okay, and then the equation, the final answer that we got was, I forgot, oh my goodness, let me go find it again. Y minus 6 equals, the slope is 1 over 4, and inside the parenthesis we have x minus 12, I believe. And the point of tangency, we said it was going to intersect these points at 6, 12. And let me take a look. It doesn't look like it. Something went wrong. Maybe I made a typo. Let me go back. Oh, I know exactly what I did wrong. Y is 6 and x is 12. I accidentally switched these two. All right, let me go fix those up. This is 12 and this is 6. Oh no, or not, oh no, oh yes, look how good this looks. I wonder if there's a way for me to just adjust the y-axis so that I can, stretch it vertically for you. But I see it, I can see that the red curve is the function, it's a square root function, and the blue line is a tangent line that is touching this point at 12, 6. But I think I'm going to switch the y-axis a little bit so that I can show you a better window. I'm going to show you a better window. Oh, how beautiful this is. Maybe I'll just make this go to 20 instead of... Oh, look at that. And I will take a picture of this. Ta-da! And then I will include this on our notes so that you guys can have a proof that we did this right. All right. And I like to check my work that way sometimes. After finding our equation of a tangent line, I graph both the original function and the equation of the tangent line that I wrote to see if they really look tangent, if the line actually looks tangent at that point of tangency. So that is it for example number 4. And we went over about 4 different examples, 3 during class and 1 in this short video. And I'm planning on picking 1 like this on your test. So for your test, I will ask you to find an equation of a tangent line using this limit definition of derivative. For a quadratic binomial, I'll make up something like this. I'll give you something like this. And I will ask you to find an equation of a tangent line at, I don't know, like a value. So I'll make up a practice problems for you guys to try as a homework. But that is it for example number 4.